Swayam Prabha. Digital India. Educated India.
Now coming to the understanding of stiffness or modulus of long fiber composites. Now here we will just try to understand axial and transverse Young module. Okay, that how to predict. So there axial means this is a composite, say, okay. This is a composite block and fibers are placed axially. When we apply stress in along the fiber orientation direction, then we will call it as axial, okay, axial loading. And when we apply load at right angle to the fiber orientation, then we will call it as transverse loading. So that we can this modulus we can predict by using simple slab model. Now see, this is the simple slab model where fiber volume fraction is F and matrix volume fraction, it's 1 minus F. Okay. And here you can see the volume fraction is represented by the proportional thickness proportion. Now here fiber volume fraction is F. So thickness is represented. This is a fiber. Green color is fiber. So here it's represented by the thickness here. So F at 1 minus F is the void part. So there are two models. One is axial loading model. First, let us discuss axial loading model, which is known as void model. And this model here, it's called equal strain model. Why is it equal strain? When we apply stress here, both matrix and the reinforcement, they will be strained with equal quantity. The strain will be equal. So this is called axial loading. Okay, and here you can see EL is the epsilon L is the strain of matrix, which is ELF is the strain of fiber. So they are equal. So strain of fiber, if we can calculate by stress of fiber and divided by fiber modulus. And as it's equal strain, so matrix strain will also be equal epsilon LM matrix strain, and matrix strain is nothing but stress on matrix by modulus of matrix, and which will be equal to the strain of composite by modulus of composite. So using this relationship, we can predict the modulus of composite if we know the modulus of matrix and modulus of reinforcement. for a composite in which the fibers are much stiffer. So normally in because it's a in a composite the fibers are reinforcement, so they will be stiffer than the matrix. So EF is much greater than EM. So the EF is much greater than EM. Okay, the reinforcement fibers is subjected to much higher stress because the fibers modulus is very high. So stress on fiber will be much higher than the matrix. There is a redistribution of load. Load will be redistributed because most of the load, when we stress the composite, most of the load will be on the fiber, and the fiber, that is reinforcement part, and the matrix will be relatively relaxed. The overall stress on the composite can be expressed in terms of two contributions. One is the contribution due to the fiber and contribution due to the matrix. Okay, contribution, the Young's modulus. So contribution due to the fiber is fiber volume fraction multiplied by stress of fiber, stress on fiber at particular time, and plus the volume fraction of matrix and stress on matrix at that particular time. So Young's modulus can now be written as Young's modulus of composite is equal to stress on composite divided by strain on composite. Stress of composite is replaced here, already it has been derived, and strain of composite is which is equal to the strain of matrix and strain of fiber. So we can use a strain of fiber, which is nothing but the stress of fiber divided by modulus of fiber. And finally, if after solving this, we get the relationship, which is the matrix volume fraction multiplied by the modulus of matrix plus fiber volume fraction multiplied by modulus of fiber, okay, which gives the modulus of composite. And this is known as the rule of matrix. Okay, and it shows that the axial stiffness is given by the weighted mean of stiffness of two components depending only on the volume fraction. So if we increase the fiber volume fraction, we can achieve more higher stiffness of the material. Now coming back to the another loading system, which is transverse loading, which is also known as Rias model. And here the assumption is that it's called equal stress system. Earlier it was equal strain system. Here the stress acting on the reinforcement is equal to the stress acting on the reinforcement is equal to the stress acting on the matrix and stress acting on the composite. So it's called equal stress method. So from this relationship we can know the stress on the composite equal to stress on fiber equal to stress on matrix. Stress on fiber is nothing but strain on fiber multiplied by modulus of fiber. Okay. Similarly, stress on matrix equal to strain on matrix multiplied by strain modulus of matrix. So the net strain is the sum of the contribution of the matrix and fiber. So that's true here. So because when we apply the load, you can see here, when we apply load, suppose this is a fiber, here is a fiber and here is a matrix system, and when we apply load in transverse direction, the total strain will be the strain of the matrix plus strain of the fiber. So here total strain of matrix epsilon 2 here in the transverse direction is a strain on fiber is nothing but the fraction. This is strain on fiber and here is the strain on the matrix. It's basically with the proportion of fiber volume fraction. Okay. So from this relationship we can calculate the modulus of, so here you can see here, so when it is strained here, so from there we can calculate the modulus. Here modulus of matrix is modulus of composite E2 is nothing but it's a modulus stress on composite, modulus of composite equal to stress on composites, that sigma 2 and divided by epsilon 2. So this is stress, so equal stress, so that stress on composite, it's nothing but stress on the fiber. Okay, sigma 2f and divided by epsilon 2, that epsilon 2 means strain on the composite which has got two components, fiber strain and matrix strain. So that is replaced here, this formula is replaced here, and from there we can get this relationship. Okay. Means fiber volume fraction divided by the volume modulus of fiber plus matrix volume fraction divided by modulus of matrix power minus 1. So this is the relationship you can get, and this is called inverse rule of matrix, and this is, it's actually poor approximation of the modulus of the composite. So it's a poor approximation. In reality, the region of the matrix in series, this is the, it is a, here the matrix in series with the fibers. Here the suppose this is a fiber, here is another fiber. Now the matrix, we can draw the matrix with the green color, these are the matrix, and the loading is done in this direction, in the transverse direction. So the region of matrix in series with the fiber close to them and lying along the loading direction are subjected to high stress similar to that carried by the reinforcement. So here the region which is close to fiber, there will be the matrix will be stressed at a very high level than the other. So here unequal distribution of stress on the matrix portion is there, whereas the region parallel to the matrix in parallel with the fiber adjacent laterally are constrained to have the same strain as that of fiber. So the portion where apart from that zone, other zone in between the fibers, so there they will not be stressed at that level also. So that's why this leads to non-uniform distribution of stress strain, okay, along the total structure, in the total structure, which means the model is inappropriate. So this transverse model is inappropriate model. Now critical length, if we can get another concept, is the critical length for discontinuous fiber. It's not for continuous fiber, and this is the length, the minimum length which can be taken out from the matrix without breakage. That's a critical length. Now the balancing force, if you can see here, the surface area of the fiber is pi d. Pi d is the circumference of fiber cross section, and dx is the length in our consideration. That's a total surface area, and here the force applied is that the stress on the fiber which is applied here, it's sigma f plus d sigma. So that is the axial tensile stress is added, okay, and that multiplied by cross sectional area of fiber, that is the total force. This force we are applying on the fiber, and that force will be, okay, restrained by the composite, because this fiber is assumed to be inside the composite. So we are applying this force, and that force is restrained by the composite by, this is tau I is the cohesion force multiplied by the cohesion force per unit surface area multiplied by surface. This is the restraint force, and here is the this sigma f force on the fiber multiplied by this stress. So this area. So this is the total balancing here, and from there we can calculate the critical length. That is, critical length is the maximum embedded length of fiber that can be pulled out from the composite without rupture. If we know the fiber breaking strain, from there we can calculate the this length dx. Okay. So here we can calculate, and on integration we will get, so this is the derivation, and if we see here from the both the sides the fiber, this is the critical length by 2, critical length by 2, total critical length will be equal to 2xc. Okay. So critical length is the maximum embedded length of fiber can be pulled out from the composite without rupture. that we have already discussed. So we can calculate the critical length and critical volume fraction. So modulus and ultimate failure stress of continuous fiber composite. So unidirectional derive the which is derived earlier, and critical volume fraction we can also calculate. So this we have already derived. So total force on this is on composite equal to force on fiber and plus force on matrix. So area of cross section proportional to volume. So this we have already derived here. Composite we have already derived the modulus of composite, stress on the composite using the rules of mixture. So here you can see here. So this is the matrix in a matrix case. So this is in a composite. Matrix is loaded when it is strained. So matrix and fibers they are being loaded. The stress strain behavior of matrix and fibers are given here. Now in this case here, strain on fiber equal to strain on matrix. So that is with that condition we have already discussed here stress component. Now for ductile matrix here, this is for ductile matrix where matrix strain breaking strain is higher than the fiber breaking strain. So strain of fiber is less than the strain, or that is ultimate strain. For brittle matrix, the strain of fiber will be more than the strain of the matrix. So matrix will be extendable. So for first let us see the ductile composite. This is the for ductile composite where strain of matrix is more than the ultimate strain of the fiber. And here if we derive at different volume fraction, we get these two relationship, and the point of intersection is the volume fraction, which is called critical volume fraction. And critical volume fraction, for the volume fraction which is more than the critical volume fraction, fiber volume fraction is more than the critical volume fraction. In that case, if we see, if it is, this is critical volume fraction here, V CRA crit. When the volume fraction is more than the critical volume fraction, we follow this relationship. This is the relationship. Okay, where delta dash M is nothing but the stress on matrix when the fibers will break. Okay, this is the relationship here, and before breakage of fiber and before fiber breakage, and when the critical volume fraction, the volume fraction is less than critical volume fraction, then other relationship will work. Okay, and for brittle matrix you can see here, for brittle matrix where the matrix ultimate stress is ultimate strain is less than the fiber. So here two relationships simply will be using here before breakage. Now let us try to solve few numerical. What weight of carbon fiber in kg with a density where 1800 kg per cubic meter is the density of carbon fiber. So what is the weight of carbon fiber must be added to 1 kg of epoxy. That is a matrix. Epoxy density is 1250 kg per cubic meter to produce a composite with density of 1600 kg per cubic meter. So here hints is that rule of matrix to be used to calculate the density. So fiber density is given and epoxy composite density is given and also matrix density is given. We have to calculate the fiber volume fraction F, that we have to calculate. Now let us see the rule of matrix is this is the rule of matrix. What is that? Density of composite equal to density of fiber multiplied by volume fraction of fiber plus density of matrix multiplied by volume fraction of matrix, which is 1 minus volume fraction of fiber. So from there, just replacing the data, 1600 is the density of composite, 1800 is density of fiber, and 1250 is the density of matrix. So by solving this relationship, we get volume fraction 0.636. So that means 63.6% fiber is there. Okay. To get weight fraction, so weight fraction is, so this is the volume fraction. Here you have to get the, what is the weight fraction. So this is the volume fraction here. To get weight fraction, the volume fraction of fiber multiplied by density of fiber by density of composite. So 0.636 was the volume fraction of fiber multiplied by density of composite is, density of fiber is 1800 divided by density of composite was 1600. So we can get the weight fraction 0.716. 7.716 the weight fraction of carbon fiber, and what we have here 1 kg of epoxy is used. So for 1 kg epoxy, what will be the weight of the carbon fiber? So weight of epoxy here equal to 1 minus weight fraction of epoxy Wm equal to 1 minus weight fraction of fiber, which is 0.716. So 1 minus 0.716 equal to 0.284. This is the weight fraction of matrix, okay, epoxy. So weight ratio here is, this is the weight ratio. From there we can calculate the weight of carbon fiber for 1 kg of epoxy. It will be 2.52 kg. So this is the way we can calculate the the requirement of carbon fiber. Okay, if we know the density, so here the rule of matrix is being used. Next is that unidirectional glass fiber epoxy composite has a fiber volume fraction 60%. So volume fraction is given. The data is given. So this is the data given. So calculate the theoretical density of composite in the fiber direction. Okay. Theoretical density of the composite. Acha, calculate theoretical density. So density of epoxy is given, density of glass fiber is given. So from this two, we will not use this two data. These are the conductivity and the modulus data. We will use simple the rule of matrix, rule of mixture we will use. This is the rule of mixture where density of composite equal to density of fiber multiplied by volume fraction of fiber plus density of matrix multiplied by volume fraction of matrix. So by solving this equation, we're just replacing the density of fiber is given 2540 multiplied by fiber volume fraction is given 60%. So 0.6 plus 1250, the density of epoxy is given multiplied by volume fraction of matrix 0.4. So we get 2024 kg per cubic meter is the density of composite. Next, calculate the flexural stress in megapascal of a unidirectional composite loaded in 3-point bending. The rectangular specimen tested has a thickness of 3 millimeter. Width of the sample is 25 millimeter and sample fails at the peak load 200 Newton. The span length was chosen to assume assuming a span thickness ratio is 32:1. That means span length will be B multiplied by 32, 96 millimeter. This is span length. Now here it's a 3-point bending. For 3-point bending, although we have not discussed earlier, you can simply refer to the earlier course on composite. So there the relationship is given here. So stress in megapascal equal to 3PL divided by 2BD square, where P is the peak load. Peak load, L is the span length, which is 96 millimeters given. B is the width of sample. Width of sample 25 millimeter is given here. So this is 96, 25 millimeter, and peak load is given 200 Newton. Peak load is given, and thickness is given here 3 millimeter. Okay, and stress is given by 3PL. Just by simply by replacing, we can calculate the stress. So here replacing, we will get the stress 128 megapascal. So this for 3-point bending, the stress is given by this relationship. For 4-point bending, there will be different relationship. Okay, and for modulus, there will be different relationship. This relationship one can easily refer to the earlier some literature, standard literature. Now calculate the flexural modulus megapascal for a sample tested in 4-point bending test. If the span length to thickness test is 32:1 and here the thickness is again 3 millimeter, span length 96 millimeter, specimen width again 25 millimeter. Here the slope of initial portion of the deflection is of the curve is 155. So here flexural modulus is given. Is asked. This is the relationship. 0.17 LQM by 4BD square DQ. So here the slope is M. Slope of the initial portion, that is the modulus of the initial portion. It's M, which is given. M is 155. Span length is 96 mm. Width of the specimen 25 mm given. Thickness is given 3 mm. This relationship, flexural modulus relationship, it's for the 4-point bending. For 3-point bending, we will have different relationship. And flexural stress is given here. This is actually flexural modulus. This is not modulus, not this. Flexural modulus. And by replacing all the data, we will get 8634.36 megapascal. This is the answer. So simply by replacing the data, so one must know the relationship here and also the what is the ratio here. Ratio has to be. Calculate the fiber volume fraction of the composite utilizing the following values. So these are the values. Weight of fiber 30.35 gram. Density of fiber is 1.5 gram per cc. Weight of matrix is 0.25 gram and density of matrix is 0.9 gram per cc, not G. This is gram per cc. Okay. Density of matrix is given and density of fiber is given, weight of fiber is given, weight of matrix is given. We have to calculate the fiber volume fraction, not the weight fraction. So fiber volume fraction is nothing but the weight of fiber by density of fiber, the volume of fiber divided by, so total volume of fiber divided by total volume of matrix, that means total volume of composite, that is volume of fiber plus volume of matrix. So multiplied by 100, that total volume fraction. So volume of matrix is weight of matrix by density of matrix. So everything is given. From there we can calculate the fiber volume fraction. So 0.35 is the weight of fiber divided by density of fiber. That means volume of fiber is we have got in the matrix divided by volume of fiber plus volume of matrix. Volume of matrix means 0.25 is the weight of matrix divided by the density of matrix 0.91. So from there we get 46% is the fiber volume approximately we'll get. And similarly we can calculate the matrix volume fraction. Next is a unidirectional composite made of carbon and polypropylene is to be utilized to the aerospace application. The experimental density for composite is 1.170 gram per cc. Calculate the white content percent for composite if the densities of fibers and matrix are 1.5 gram per cc and 0.9 gram per cc respectively, with a fiber volume fraction 0.5. That means fiber volume fraction 0.5 means matrix volume fraction will be also 0.5. So here we have to calculate the experimental density, calculate the white content percent. So densities are given. So white content is equal what theoretical density minus experimental density divided by theoretical density. That is the, and if we multiply by 100, it will be percent volume fraction. So theoretical density, this is void content for a composite. Okay. Experimental density. So theoretical density is, we can calculate by using the rule of mixture. Theoretical density of composite. Okay. It's a density of fiber 1.5 multiplied by volume fraction, that is 0.5, plus density of composite, so density of matrix multiplied by 0.5. So we will get the theoretical density of composite. The theoretical density of composite comes out to be 1.20. But here what we are getting, experimental density of the composite is 1.170, which is lower than the theoretical density. So that means there will be some void present. So void content will be the difference in density divided by the theoretical density multiplied by 100. So difference in density is the 1.2 is the theoretical density. Now it's a theoretical density minus 1.17 is the actual density. This experimental density divided by 1.2, and that from there we can get the void content. 2.5% is the void present. Due to that, the density has reduced. Otherwise, density should have been 1.20 if there is no void present. So our target should have been 1.20 here. Now, and the next numerical, for a unidirectional composite made up of carbon fiber and polypropylene matrix, where PP matrix was dissolved by liquid digestion method. So PP matrix has been dissolved. Weight of composite prior to liquid digestion was 10 milligram. 10 milligram was the weight of composite. So weight of composite was there. On liquid digestion, the weight of fiber remaining was 6. So 10 gram. So 10 gram was the composite. After digestion, liquid digestion, 6 milligram fiber remained. Rest 4 milligram was the composite. So it's a very simple, and matrix weight. Sorry, 4 milligram was matrix. So very simple. So matrix weight percent, it will be typically 40%. So weight of matrix divided by weight of fiber plus weight of matrix total. So 4 by 10, so 40%. 40% was the matrix weight percent. Now next is the reinforced plastic sheet. is to be made from a matrix with a tensile strength 60 meganewton per square tensile strength. Okay, continuous glass fiber with a modulus of 76 giganewton per square. So if the resin ratio by volume is 70%, so resin ratio by volume percent 70%, that means fiber volume fraction will be 30%, and fiber to matrix modulus ratio is 25. So fiber modulus is 25 times higher than the matrix. Then the tensile strength meganewton per square meter and modulus of the composite will be. So we have to calculate the tensile strength of composite and modulus of composite. Okay. So fiber modulus is given, glass fiber modulus is given 76 giganewton per square meter. So composite that matrix modulus will be 25 times lower than this. So only here matrix strength is given. So when we have to calculate the tensile strength of composite, so matrix strength is given, but the matrix strength is giving 60 meganewton per square meter, but fiber strength is not given. So we need to calculate the fiber strength. So the stress on fiber we have to calculate. Here, since we are using the rule of mixture, the strain of composite equal to strain of matrix equal to strain of fiber, then we get this relationship: stress on fiber equal to stress of matrix divided by multiplied by modulus of fiber by modulus of matrix. So this ratio is given as 25. Here it's given 25, and stress of matrix is given 60. So 60 multiplied by 25 will be the, this is here, this is the fiber. Okay, 60 multiplied by 25, this is the for stress on fiber. So stress on fiber multiplied by volume fraction is given here. So volume fraction, it will be 3. Here it's given 60 multiplied by 0.7, and this is nothing but 60 multiplied by 25. So from there we can get 60 multiplied by 25 multiplied by 0.3, this is 25, 60, and here 60.7, we will get the tensile strength. So tensile strength we have got 492, and then modulus we can simply use the rule of mixture. We know the modulus of fiber, modulus of matrix we know, and volume fraction we know. From there we can calculate. So this is the modulus of fiber is given. Glass fiber conduction modulus 76 multiplied by 3.3, and this is the modulus of matrix 76 divided by 25 and multiplied by volume fraction of matrix. So we get 24.93 giganewton per square meter. This is the composites modulus. These are the two answers. Next, in a unidirectional Kevlar epoxy composite, the fiber to matrix modulus ratio is 20 and the epoxy occupancy is 60%. So 60% by volume. So volume fraction of epoxy, that is matrix, is 60% and fiber volume fraction will be 40 or 0.4 and V matrix will be 0.6. If the modulus of epoxy is given 6 giganewton per square meter, then modulus of composite. So it's very simple. The modulus of fiber we can get. So modulus of composite epoxy is given. Modulus of fiber 6 multiplied by 20. 120 is a Newton per square meter is the modulus of fiber. Our modulus of matrix is given as 6. Okay, and using this relationship we can calculate simple calculation. 120 multiplied by 0.4 plus 6 multiplied by 0.6, it is coming out to 51.6 giganewton per square meter. Okay, and next is that consider a unidirectional composite material loaded in the direction of perpendicular to the axis of the reinforcement. This is perpendicular to the axis. So it will be inverse rule of mixture will be used here. The modulus of reinforcement is 100 gigapascal and that of the matrix is 10 gigapascal. If the volume fraction of the reinforcement is 50%, that means fiber volume fraction is 0.5 and the matrix volume fraction will also be 0.5. Then the modulus of the composite in transverse direction. So we will be using the inverse rule of matrix. So this is the composite modulus. So using the inverse rule, this is the relationship where EF is the fibers modulus, EM is the modulus of matrix. So using this relationship, we can calculate the modulus of composite in transverse direction. This is as per the inverse rule of mixture that we have already discussed. And the last one is that unidirectional carbon fiber epoxy composite has a fiber volume fraction 60%. The data given, calculate the conductivity of the composite fiber in the fiber direction. So using the rule of mixture, we can calculate also the thermal conductivity of fiber. Same rule of mixture which we use for measuring the density, measuring the modulus, measuring the tensile stress. Okay, so the same formula if we use here, this is the conductivity of fiber multiplied by volume fraction of fiber, conductivity of matrix and volume fraction of matrix. So that we use the same rule of mixture. So we will get the value 0.73. Okay, is the conductivity of the thermal conductivity of the composite. Okay, and that's all about the analytical approach on composite testing. Thank you.